All right. Welcome back, everyone, for another deep dive.
Yeah.
This time, we're looking at RNNs.
Recurrent neural networks.
Exactly.
Yeah.
And in particular, this paper is about a model called HGRN2.
HGRN2.
We've got the research paper right here.
Awesome.
And this is pretty dense stuff, so hopefully we can unpack it a little bit today.
Absolutely. Yeah, we'll break it down.
So right off the bat, they jump into talking about how HGRN2 is improving upon its predecessor, HGRN.
The first one.
And they're really focusing on the recurrent state size, which they want to make bigger.
Okay.
What exactly does that even mean? What is recurrent state size? And why is it a big deal?
Yeah. So the recurrent state size, you can kind of think of it like the memory of the model.
You okay?
So as the network is processing information, like, words in a sentence or data points in a time series,
Right.
this state, this recurrent state, is storing what it's seen so far.
Gotcha.
So the bigger the state size, the more information it can hold in its memory, which means, in theory, it can understand more complex pattern, more complex relationships in the data.
So it's like upgrading the RAM in your computer, right?
That's a great analogy, yeah.
You have more RAM, you can run more demanding programs, do more things.
Absolutely, yeah.
So they've managed to expand the memory in this HGRN2, but how does that translate to, better performance? What does that actually look like?
Yeah, so imagine you're using an AI chatbot and you're having a conversation with it.
Okay.
A larger state size would allow that chatbot to remember more of your previous conversation.
Right.
And therefore, it could give you more natural and more coherent responses.
That makes sense.
Because it's actually following the thread of what you're talking about.
It's not just looking at your last sentence. It's got that context.
Exactly.
Okay. That makes a lot of sense. But how do they achieve this larger state size?
Right.
They mentioned something called the outer product method, which sounds kind of intimidating.
Yeah, it sounds scary, but it's not too bad. The outer product, it's basically a mathematical operation they use to expand the state size.
Right.
So imagine you have a list of features that describe a sentence.
Okay.
Like the overall sentiment of the sentence or the topic of the sentence.
Right.
And then you have another list of features for each word in the sentence.
Yeah.
Like its part of speech or its meaning.
Okay.
The outer product combines these two lists. Essentially, it creates a grid showing how each sentence feature interacts with each word feature.
Gotcha.
And this grid, with its much larger dimensions, becomes the expanded state of the model.
Okay, I think I'm starting to see the picture here.
Yeah.
But wouldn't that mean a larger state size means more calculations, which means it would take a lot longer to train?
Yeah, absolutely. That's a major challenge
Right.
because you're having to process and update this much larger grid of information every time the model sees a new word.
Right, right.
So it's definitely going to take more time and computational power.
So they've expanded the memory, but at the cost of speed.
Right.
That doesn't sound like that much of an improvement.
Well, that's where HGRN2 gets really clever.
Okay.
They came up with a solution using what they call a multi-head approach.
Right.
It's inspired by linear attention models.
Okay.
Essentially, they found a way to split the workload.
Right.
So that training becomes more efficient even with this much larger state size.
So it's like having a team of chefs in the kitchen instead of just one chef trying to do everything.
Exactly, yeah.
Okay.
They're dividing the large grid of information into smaller chunks, and each head, as they call it, processes one of those chunks simultaneously. So they're doing all this parallel processing that allows them to train this much larger model without sacrificing speed.
Okay, so they're able to have their cake and eat it too.
Right.
They get that larger memory capacity, and they keep the speed.
Exactly.
But the paper also mentioned something called GLA.
Okay.
Or gated linear attention. And it sounds like that's also trying to solve a similar problem, but with a different approach.
Yeah, so both HGRN2 and GLA are really focused on controlling the flow of information within the network.
Okay.
But they do it in slightly different ways.
Okay.
So imagine like a traffic cop at a busy intersection.
Okay.
GLA's approach is kind of like having the traffic cops stop cars before they enter the intersection to prevent congestion.
Okay. So GLA is all about preemptive traffic control.
Right.
What about HGRN2?
HGRN2 is more like having the traffic cop control the flow further up the road, preventing congestion before it even reaches the intersection.
Okay.
It applies its forget gate to the previous state before incorporating new information.
Interesting. So they're both directing traffic but with different strategies.
Exactly.
It seems like these subtle differences in how they manage information can have a big impact.
Absolutely.
But how do we know which approach is better? Did they actually, put these models to the test?
Oh, yeah, for sure.
Okay.
They tested HGRN2 on a variety of tasks, like language modeling, image classification, and even tasks that were specifically designed to see how well it handles long-range dependencies,
Right.
which is something that traditional RNNs have always struggled with.
Okay, let's talk about the language modeling stuff first.
Okay.
The paper mentions these benchmarks, Wikitext 103 and the pile.
Mm-hmm.
What are those exactly, and how did HGRN2 do?
So Wikitext 103 is basically a huge collection of text from Wikipedia articles.
Okay.
It's like a standardized test for language models. You know, you can see how well they understand and generate human-like text.
Okay.
The pile is even bigger and more diverse.
Okay.
It's got text from all sorts of sources, like books, scientific papers, code, web pages.
So Wikitext 103 is like a focused exam, and the pile is like the comprehensive assessment.
Exactly.
Okay, and how did it do?
So on Wikitext 103, HGRN2 got a really good perplexity score, which is a measure of how well a model predicts the next word in a sequence.
Right.
And it was competitive with other leading models.
Not bad.
And on the pile, it actually outperformed its predecessor, HGRN.
Okay.
And it also showed some promising results compared to other state-of-the-art models like Transformer++.
Wow. Okay, those are some good results.
Yeah.
But it sounds like the real test was this long-range arena thing.
Right. Yeah, the LRA.
They really wanted to see if this thing could handle those long sequences.
Exactly.
That have traditionally tripped up RNNs.
Yeah, the LRA is like an obstacle course designed to specifically challenge a model's ability to handle long-range dependencies.
Okay.
So it's like, trying to understand the last sentence in a really long paragraph.
Right.
You need to remember the context from the beginning to make sense of it.
Right. Yeah.
And HGRN2 showed that it was capable of handling those challenges.
So they've finally given these models a memory upgrade worthy of a supercomputer.
Yeah.
But let's switch gears a little bit, talk about the image classification stuff.
All right.
They mentioned ImageNet1K, which, if I'm not mistaken, is a massive data set used to train models for, like object recognition.
Yeah, you got it.
Okay.
It's a really important benchmark in computer vision.
Right.
Used to train models to recognize 1,000 different object categories.
Right, like cats, dogs, cars, that kind of thing.
Exactly, yeah. All sorts of everyday objects.
Okay.
And HGRN2 showed that it's not just good at language, it can do images too.
Okay.
It got some impressive accuracy on ImageNet1K.
Okay.
Even outperforming some convolutional neural networks. CNNs.
Wait, hold on.
Yeah.
It beat CNNs at their own game.
Well, yeah, it's pretty significant.
Yeah, because CNNs have been the go-to for image processing for years.
Right, right.
Okay, so what's going on there?
So while CNNs are really good at processing visual data, they can sometimes struggle to capture these long-range dependencies, which are really important for understanding the context of an image. HGRN2, with its enhanced memory capacity, kind of shows that RNNs can be powerful tools for image analysis, too.
Okay, so it's like they're proving that RNNs can step outside their comfort zone and excel in these new areas.
Yeah, exactly.
But you mentioned earlier that HGRN2 is a linear model.
Right.
What does that mean exactly, and why is it important?
So in the world of neural networks, linear refers to the type of mathematical operations that are used within the model.
Okay.
Linear models are known for their efficiency and speed.
Okay.
Because they rely on relatively simple operations like matrix multiplication.
They're like well-oiled machines. They process information quickly and efficiently.
Exactly, yeah.
Okay.
And that efficiency makes them really attractive for real-world applications where speed is critical.
Makes sense.
But traditionally, they've been considered less expressive than nonlinear models.
What does that mean?
So it means they might not be able to capture all the nuances and complexities of certain data patterns.
So it's a trade-off between speed and expressiveness.
Right.
Linear models are fast, but they might miss some details. Nonlinear models are more powerful but slower.
Exactly. And that's why HGRN2 is so interesting.
Right.
Because it kind of achieves both the efficiency and the expressiveness.
So they found the holy grail of machine learning, speed without sacrificing accuracy.
They're getting closer.
But even with all these advancements, the paper kind of hints that there's still room for improvement.
Yeah.
Especially when it comes to handling these really, really long sequences.
Right. The authors acknowledge that linear models, including HGRN2, still face challenges when you get to these really long sequences,
Okay.
even with the state expansion and the multi-head approach.
So it sounds like the quest for the ultimate memory machine continues.
It definitely does.
So it seems like we're on the verge of some pretty amazing breakthroughs in AI, but there's still some challenges they got to figure out.
Definitely.
When it comes to these RNNs and models like HGRN2, what are some of the big questions researchers are like grappling with right now?
Well, I mean, one of the biggest is still like how to handle those really, really long sequences we were just talking about.
Yeah.
Even with all the cool stuff in HGRN2, there's still a gap between what these linear models can do and the more computationally intensive models like transformers.
Okay.
So researchers are looking at new architectures, new ways to train these models, even hardware optimizations, just to try to bridge that gap.
So it's like a race to build the ultimate memory palace.
Yeah, kind of.
One that can store tons of information and retrieve it super fast.
Exactly.
What else?
Yeah.
What else are they working on?
Another really important area is interpretability.
Okay.
So as these deep learning models get more and more complex,
Right.
it gets harder to understand like how they're actually making decisions.
Yeah, it's like a black box.
Right,
So
exactly.
you put something in, you get something out, but you don't know what's happening in between.
And that can be a real problem, especially in areas like, healthcare or finance.
Where trust and accountability are super important.
Right. You need to know why the model is doing what it's doing.
Exactly.
So how do they fix that?
Well, they're developing techniques to try to peek inside these models to better understand their decision-making process.
So it's like they're trying to decipher the inner workings of like a brilliant but mysterious mind.
Yeah, that's a good way to put it.
You see all these amazing things it can do, but you don't know how it's doing it.
Exactly.
So it sounds like there's still a lot of work to do.
Oh, yeah, absolutely.
But it also seems like RNNs have the potential to go way beyond just these language and vision tasks that we've been talking about.
For sure.
What other areas are researchers looking at?
Well, they're exploring RNNs for things like robotics, music generation, even scientific discovery.
Wow.
The versatility of these models makes them a really powerful tool for tackling all sorts of problems that involve sequential data.
So they're more than just a one-trick pony.
Exactly. Yeah. They can do all sorts of cool stuff.
And the future of RNN research is really exciting, I think. It's a rapidly evolving field. We can expect to see a lot of really interesting breakthroughs in the years to come.
Well, this has been a really fascinating deep dive.
Yeah.
Into the world of HGRN2 and RNNs in general.
Absolutely.
I feel like I've learned a lot.
You too.
Even if my head is spinning a little bit from some of the technical details.
Yeah, it's always a journey of discovery, right?
It is. It is.
The more we learn,
yeah,
the more we realize how much more there is to explore.
Well, if this deep dive has piqued your interest, I definitely encourage you to check out the full HGRN2 research paper.
Absolutely.
And who knows, maybe you'll be inspired to contribute to this amazing field yourself.
You never know.
So until next time, keep diving deep and never stop learning.
See you then.